Hi everyone and welcome to CPE EE329. My name is Joseph Cayenis and I will be your instructor for this quarter. In this lecture I'll give an overview for the course. Specifically I'll describe what embedded systems are and what are some of their key characteristics. I'll then give a brief overview for the structure of the class and the lab and introduce the microcontroller, the MSP432 that we'll be using for our assignments and labs for the quarter. So let's talk a little bit about computing. As I'm sure all of you are aware, computing is really happening all around us in so many different facets of our lives. From our personal electronics, our mobile devices, our personal computers, our laptops, to server systems and the cloud, industrial applications, entertainment, and many others. And the exciting thing moving forward is that there are a whole host of other applications that are also emerging, including autonomous vehicles, artificial intelligence, biomedical devices, robotics. The wide range of computing applications and systems has also given rise to a wide range of approaches to designing and implementing these systems. So one approach that we can use to build these systems is using application-specific integrated circuits, or ASICs. And this is really the best choice when we want to really get the lowest power and the most energy efficiency for our application, is to actually fabricate a chip. The downside for this is it takes a long time to actually design, fabricate, test these types of systems. You can think on the other side of the spectrum are general purpose processors, multi-core processors, for example, that you would find in your mobile home computing machines. These offer much higher performance and general performance, allowing it to be programmed and execute a wide range of applications efficiently. Embedded microcontrollers, you can sort of think of sitting in between these. It's also a programmable general purpose processor, but what typically has tight resource constraints and is designed for low power and energy efficiency, as well as reduced cost. So among the different computing domains or designs, embedded systems have actually shown the greatest growth over the past decade. And that's what's shown on this graph. On the x-axis here is over the years from 2003 to 2017, the total revenue from each of the microprocessor types. And so you can see that embedded processors have really become an important part of the computing landscape in our daily lives. Okay, so what is an embedded system? So we call it embedded because these processors are usually embedded or a part of a larger system or a larger machine, including sometimes mechanical components and other physical design elements. It usually also includes a combination of both hardware and software. Some parts of the system implemented using software, some with discrete components, and some with other types of hardware. You'll sometimes also see these systems described as cyber-physical systems, as they merge both computing aspects, communications, wireless, processors, software, with physical components. So what are some characteristics for these types of embedded systems? Well, as I said, usually these processors are part of a bigger physical system, including different types of peripherals, actuators, and sensors. Many times there are also real-time constraints. So certain tasks within the system have to be done at certain time intervals. Otherwise the system can fail. Many times these systems are power constrained. So they're maybe powered by batteries, and they need to consume the least amount of energy as possible in order to increase the lifetime of the device. They may also be size constrained. And for many of these systems, there might also be important reliability and security constraints. They might be a mission-critical application. And then the last point here is that many times the time to market is critical. For many companies, they cannot take years to develop a new architecture, a new ASIC to produce the application. So let's talk about a couple examples of these applications. Cars for a long time have included microcontrollers as part of their system. Things like engine fuel injection, transmission control, and many other important systems have that. And today, with autonomous vehicles, there are a whole range of important subsystems where microcontrollers are sensing and making decisions. You've probably all seen home appliances that are now also typically including more sophisticated microcontrollers, sports equipment, and increasingly biomedical applications. And in this area in the past years, we've seen a growth in terms of implantable devices where we put these embedded microcontrollers actually inside our bodies, and many other applications, including in robotics and increasingly within different aspects of our cities and our societies. So as another example, systems are increasingly including sensor networks. These are really low power embedded systems that usually include many distributed sensors and may also use something called energy harvesting, which we'll talk more about later in this course, to gather ambient energy and power the device to make it sensing and communicate those measurements. And so these can include things like monitoring animal migrations and other agricultural applications. These may also be sensors that are embedded inside structural components, such as the concrete of a bridge. The idea being that these sensors can monitor the stresses and the health of the material over the lifetime of the bridge. And so the picture on the right here is an example of this, something called the Intel WISP. And this embedded systems has a very low power system that is actually powered by RF. Sort of like you've probably seen before with RFID if you've gone through the toll before, for example. An RF signal actually allows the device to power up, take some measurements, and communicate it back. There are also many other interesting applications, so I'll include 2 links here in the slides. One, which I think is a great example of a resource-constrained embedded system, which is aerial autonomous vehicles, or UAVs. The first one is quadcopters doing some interesting tasks, and these are systems where weight is critical in order so that they can fly and also be responsive. And so several trade-offs have to be done in order to keep the system feasible within its weight constraints, but also giving it good performance. And the second video is another example of this, a DARPA project for a very tightly energy constrained UAV that can fly into buildings and record. Okay, so in general then, some important microcontroller characteristics for these embedded systems is the fact that they're usually integrated. So in addition to a general purpose processor, they also have several different types of peripherals or hardware that does specific types of tasks like timers and communication interfaces and encryption and so forth, actually on the same chip. These microcontrollers are also typically low cost given they have to be typically used in a large volume of applications. They typically have lower clock frequencies compared to other processors that you've probably worked with. So for microcontrollers, the typical range is maybe up to 100 megahertz. They typically also are built with power as a first order design consideration, meant to be in low power applications, which may be battery powered. The processor design itself might have less optimizations. The data instruction word sizes might be smaller, 4 bits to 32 bits. They typically also are limited in memory, and this has historically been true as embedded systems had very small memory sizes. And finally, they typically have some flexibility in how input and output can be configured with the different pins on the chip. Some microcontrollers having up to 150 pins. This is going to be a big part of this course, is actually designing these systems, both the hardware and the software. By the end of this course, you'll be able to design and implement C programs for embedded systems, including using some important microcontroller peripherals like timers, generating PWM signals. We'll learn about how to interface with the microcontroller, including using common protocols like SPI, I2C, and UART. We'll learn about mixed signal design, analog to digital and digital to analog conversion. And we'll also learn a lot of really important skills for designing, implementing, and testing embedded systems. We'll evaluate the trade-offs with performance and power for these systems. We'll talk about some important design approaches. We'll see how we can interface with many different types of components. A big part of this class will also be reading and learning how to read and understand a data sheet. And we'll also have the opportunity to improve our awareness of ethical responsibilities of an engineer. So a big part of this course is the lab. We'll have 4 big projects, the 4th being the final design project of your choosing. And for each of these projects, we'll have several assignments that build up to the bigger project. Okay, so let's talk about the microcontroller that we're going to use. So this is the Texas Instruments microcontroller, and it has an MSP432 chip on this PCB. As part of the MSP432, the processor is an ARM Cortex M4. It has 256 kilobytes of on-chip flash memory for code and 64 kilobytes of on-chip SRAM for data. And then we'll talk some more about the on-chip peripherals that it has. For software, we're going to be designing using the C programming language, and the IDE, or the interface that we'll be using to develop our code, is the Code Composer Studio CCS. So the launchpad for the MSP432, as you can see here, a big part of it is the actual processor, the MSP432, along with supporting logic. So we have the power system on the top left here, an onboard debugger, programmer, and a handful of jumpers and other pin connections. So as a quick review, the processor, if you remember from 233, has a CPU. This is sort of like the brains of the system. and where our code is going to run and be executed. Now, there are different ISAs the system can use. We're using the ARM ISA. It's a very popular ISA for embedded systems. Other ISAs, such as RISC-V, are also becoming very popular. The CPU itself has an arithmetic logic unit where the actual instructions are executed, as well as a set of registers for holding the program's intermediate state. Another important piece for many embedded systems are interrupts, and we'll talk more about this quarter, how the interrupt controller works for the ARM M4. Now, this CPU is connected through a bus, an interconnect, to the memory. The memory holds both our program and our data. And for our microcontroller, as many others, we have one type of memory technology typically holding our instructions and one that typically holds our data. Flash for our instructions and RAM for our data. Systems may also include other types of non-volatile memory that can hold important data even after the power is removed. Connected to this bus are also several peripherals or special hardware circuits that are supporting the operation of the system. Things like communications, timers, analog digital converter. And then because these systems are very commonly used to interface with physical components in the outside world, there's some type of I/O, and we'll talk more about that in the coming lectures. Okay, so this is the MSP432 microcontroller pulled from the technical reference manual. And as you can see, we have several different subsystems here, but it's the same basic architecture as the previous slide. So we have our CPU in the bottom left, the ARM Cortex M4. We have our bus, the line that goes around the system, connecting the CPU to the different types of peripheral devices and I/O, as well as our memory. So the right-hand side of the diagram here, we have our different types of memory, the flash, SRAM. We have some logic for adjusting the power for the chip. We have a clock system with different configuration options. We also have a set of timers, including a real-time clock, a watchdog timer. We have special logic for the processing of analog signals and other types of input, output, and communication interfaces. Okay, so this is an important diagram that shows us what are the potential connections that we can make between the logic that's on the MSP432 and the different peripherals and those external pins. And so we'll discuss some more about this in the coming lectures about ports and how we interface. But one thing that should stick out to you right away is to notice that several pins have actually several different internal functions that they could be configured to connect to. Okay, so let's talk finally just a little bit about the course in general. We're going to cover a lot of material in 329 with many different hardware and software components. Now, there is a lot of material you're going to need to learn, how peripherals work, for example, and then there's also going to be some material that you're going to need to know how to find and use. In general, I would suggest to treat 329 as an opportunity for professional development. You should really be working to make your projects portfolio worthy, something that you can be really proud of and put on your CV and potentially show when you have future interviews. You might even want to document your projects on a blog, a website, or a video. Okay, so there are now a couple important documents that you're going to be using throughout the quarter. This includes the data sheet for the MSP432, as well as the data sheets for the different peripheral devices which we'll be working with. I would highly recommend you start to get comfortable with this information and start reading it. In fact, this will be the first assignment, which is due this week. There's also the MSP432 Technical Reference Manual, which is a very large document that has a lot of really useful and important information. This is also posted on Canvas, and you can also find this by Googling for the MSP432 Technical Reference Manual. I would also suggest that you get a lab or project notebook. This is a great skill to have, and I highly recommend you start doing it for this course. Okay, for the hardware components, in addition to the microcontroller, breadboard, and other discrete components which are posted on Canvas, you should have also received the emails about acquiring an analog discovery component, which we'll be using as an oscilloscope and logic analyzer for the course. As I mentioned earlier, we'll be using the Code Composer Studio CCS. The latest version is version 10 for doing our code development. And so you should also download Code Composer Studio on your personal machines.